Okay, circle theorems, and you've got lots of information here, but all of that is on the diagram, so you can either cross it out or just ignore it. That's on the diagram as well, because it's clearly labelled, and we've just got to prove that this angle CDA, which is that one there, is equal to 2x, giving reasons for each stage in our working. Got to take that bit seriously. Right. This is to do with alternate segment theorem, this problem. Alternate segment theorem works like this. It's where you've got a tangent, which is this line here, just glancing off the circle, and a triangle in the circle that touches the circumference of the circle at the same point that the tangent does. And when you've got that arrangement, you can say that those two angles there are equal. And kind of symmetrically, those two angles there are equal. Now, with a bit of practice, you can quickly just identify these, just going back to these two black ones. To work out the angle that you want, once you've got an angle between a tangent and one of the lines of the triangle, look at the triangle. There's three angles in the triangle, but only one of them doesn't touch this side. Because it's not that angle there, because that touches this side. It's not this angle here, because that also touches this side. It's got to be the other one, so it's that one there. So that's the idea, really, now, to work out which one it is. And with the red one, it's called the alternate segment, because it's the angle in the alternate segment. If you split up the circle using this as a chord, then in one segment you've got this angle, and in the opposite segment, which is this major segment, this huge bit, here, all the way around here, this big slice of cake, it's the angle in there which is equal. Here's another example of alternate segment theorem at work. Same idea, just different, slightly weirder shape of things, but you've still got a tangent and you've still got a triangle that touches the circle where the tangent does, and therefore we can say those two angles are equal by the alternate segment theorem, and those two angles are equal by the alternate segment theorem. Right, that's enough of the background theory. How are we going to use that in this problem here? Well, there's a bit of a clue, isn't there? You're dealing with a quadrilateral. It's actually a cyclic quadrilateral, but we don't know any of the angles in there at the moment. But look, you've got this clue here, two equal length lines, and often a trick with these problems is to draw a line in the triangle. So let's draw that line AC in there, which splits our quadrilateral into two triangles, but crucially this is now an isosceles triangle, which is going to be useful in a minute. And if we look at this triangle ABC, we can spot by alternate segment theorem that that angle at the top there must be x. And don't forget, before we go any further, well actually I'd probably finish the problem then come back and write the reasons down in an exam, because I'd want to be comfortable that I was actually on a path to the solution. But that would be what you'd write. We can then use the fact that it's an isosceles triangle to write that that angle there is x. Just give the reason for that as well. Don't just write isosceles triangle, you need to write this whole thing here. Base angles in an isosceles triangle are equal. You do need to say the base angles, because it's obviously not all three. Right, you've got an option here, well, you've got two options. Number one, this is actually my preferred method, but I didn't see many candidates doing this. You look at the triangle ACD, and then you spot that we now know this angle here is 2x. And by alternate segment theorem again, but this time for the red triangle, we can just instantly say that that angle CDA is 2x. Your reason would be CDA equals 2x, and again just alternate segment theorem. Alternate segment theorem is the only theorem for which you're allowed to write the name of the theorem as the reason. With all of the other theorems, you have to write things like angle in a semicircle is 90 degrees, or opposite angles in a cyclic quadrilateral add up to 180 degrees. You can't just say cyclic quadrilateral, for example. With this one, you can just say alternate segment theorem. The reason why they accept that is because the text for it is just really long and po-faced. Here is the alternative method you might prefer. So once you get to this stage here where you've got your two x's there, is to work out the third angle in that triangle, which is going to be 180 minus 2x, and then use the cyclic quadrilateral rule, just to write down that that's 2x there. So ADC is 2x because opposite angles in a cyclic quadrilateral are equal, sorry, add to 180 degrees.